Other weird thing is that when you do transverse tining, if vehicles start to lose control, so the tines are in this direction, vehicles start to lose control, especially light vehicles like motorcycles. The tines are in the other direction, so they start to go sideways at all. The tines promote them to spin around. If the tining is in the direction of traffic and you start to spin, it grabs you and pulls you back forward. So it's taken us a while to get to this point. Longitudinal tines are the standard now, pretty much in the US. They also happen to be significantly quieter than transverse tines. Transverse tining is about the loudest texture you can build into a roadway. So if you're using transverse tining, consider using something else. Exposed aggregate, we've done this some in the US. That's a euro, that looks like a Czech, what is it, Czech crown? So these are European photos. We don't do it that much in the US. It's costly. You have to have a good handle on this aggregate gradation. As soon as they place the concrete, you have to spray the surface with the retarding agent to slow down the hydration just at the surface. And then at the right time, you have to go back with brooms to mechanically remove that paste. If you go too late, you don't get as exposed of a surface. If you go too early, you start to pull up the rocks. So it's very much an art type thing. They do it for the reasons of noise more than anything. I guess in UK they'll do it for friction as well, but they do it mostly for noise reduction. So finally, onto the most aggressive surfaces that we can build. Diamond grooving. So we didn't do anything to the surface. We've just now, where the surface is, cut into it at a regular spacing with diamond blade saws. This one's in longitudinal direction. Concrete airfields, it's not uncommon to see some diamond grooving in airfields. Last thing, probably the most aggressive texture, diamond grinding. And we do this a lot in the US, especially in the preservation and maintenance side of things. This is comparable to refinishing a hardwood floor. So we're covering up the entire surface, or removing the entire surface defects. So if you had a little bit of faulting from slab to slab, it would zero that out. It would make the pavement perfectly smooth. Because we're making it so smooth, we also groove in negative texture as well, similar to the diamond grooving. Now what you see here is the ANSI view. So these are our aggregate here. It's very close at the surface. This is the next generation concrete surface course, INGLES, which we engineered at Purdue University and some other spots. Was Paul Donovan, is he going to be here at the Congress? Do you know? He's one of the people that worked most on this. We engineered this to be the quietest texture that we've ever had for concrete. It's as quiet as the quietest asphalt pavements, the open graded friction courses. Now, because we are finishing the entire surface, it's relatively costly relative to the other methods. But it gives us an opportunity to extend the life of the pavement. In some states like Washington and Utah, they're now taking this approach. Because they have a lot of studded tires in the mountains, so whenever it snows and there's ice, they remove their tires and they put on tires with little metal studs for traction. And those tires rut concrete. Doesn't matter. Concrete will rut just like asphalt. So what they're doing from a management perspective is if they need 20 centimeters of thickness, they'll build it just a little bit thicker than that. So they're building in some sacrificial thickness to allow them to do diamond grinding once the rutting has occurred. So once they get more than, 10 millimeters of rutting, then they diamond grind the entire surface, but they built in that extra thickness just to have that as part of the preservation. That little bit additional cost of concrete up front saves them from having to reconstruct that pavement. All right, I got 2 videos of US practice. Can we dim the lights? It's good timing that he's there. Can you ask in Spanish, Mauricio? Can he dim the lights? guess that's about as good as we're getting now. So this first video is from the Chicago area. Concrete's being delivered by a ready-mix truck. So here they're actually making bigger mounds than I would like to see. This is a low-volume project. It's a local road, so they're not necessarily getting up to the types of volumes and paving speeds that we're looking for in super high production. There's that rocket launcher. We'll see that in some other videos. So that goes out. Behind the pan, engages the tie bar, and just punches it in at the right moment. Now, if you're close enough, and you've never been around a slip-form paver before, just kind of feel how this concrete, all by these vibrators alone, is just getting pulled into being flat. And right through here, you don't see this rough aggregate texture at all. It's becoming temporarily fluidized inside of it. And that's constantly rolling that head of liquid concrete forward. They did this with GoPro cameras, so they could lose them. Past that point, they had the texturing and curing and other operations. You see our string line that's guiding the pavers. You see all those pieces of equipment mentioned. Next video is a little bit longer with the paving action. So that was Dottie Avenue in Chicago. This video is from Guntert and Zimmerman. Primary slip-form paving manufacturers are Guntert and Zimmerman, Gameco, and Power Pavers, I believe. Yeah, those, well, I guess Wirken as well. Wirken out of Germany, so there's 4 primaries. So this is their mid-size paver. This is probably one of the more popular pieces of equipment that they have. I think that this one actually has a dowel bar inserter in the video. These are just from YouTube. Just grab them off of there. We got our string line making a curve there. This piece of equipment is outfitted with a plow instead of an auger, so we'll get to see that in action. They're dumping it pretty close to where the plow will be, using ready-mix trucks, even though it looks like this project's pretty far in the middle of nowhere. There's one perspective of the plow. Once they get moving, that'll push the concrete back and forth and into the corners. There's our operator up front telling the plow to go back and forth, checking on the supply of things. Looks like here they're just getting off the header. So even out front, you can see there's a bit of a pitch to those pans. That's the drive system for the plow itself. So they're getting a pretty constant level of that concrete across the width. So you won't see that same impact of the fluidization that we saw in the last video, because things are already relatively flat. But there you see inside of the side forms, the concrete is bubbling. We're losing air because we're fluidizing with the vibrators. So it's about 2% loss of air inside of the paver. This device right there, that wheel was timing the tie bar inserter. There you can see the edge slump happening in real time. So imagine trying to pave up next to that. You have to match elevation. You want that thickness. Lots of little moving parts. But what you don't see in the slip forming action is a lot of labor. So in places like the US where labor is very, very expensive, it's more cost effective to go into some of these slip form approaches. Now when we talk about international practices, we'll see some more photos of the impact of labor in fixed form versus even precast concrete paving. So we placed the concrete. It's all consolidated, all these things. Now we're on to curing it. Now when it comes to curing, we're trying to maintain both the moisture content and the temperature of the concrete. Depending on if it's hot or cold outside, that means different things. But ultimately, the hydration reaction, so the cement plus water turning into concrete, needs moisture to happen. It needs that water. So if we lose a bunch of water, hydration will stop. If it dries out at the surface, again, the most critical spot in that thickness, that's what's exposed to traffic. That's what's exposed to any sort of salting and freeze thaw. If it dries out at that surface, hydration will stop. and we'll stop gaining strength right at the surface. So we want to make sure we either keep a constant supply of water at the surface or prevent the moisture from evaporating, which is more of what we do in pavements. The other side is temperature. If it's cold out, we want to make sure we keep it warm enough so that the concrete hydrates as we intend. In extreme cases, if you place fresh concrete in the field and it gets very cold overnight, the water might actually freeze before the concrete sets. That free water that hasn't yet hydrated with the cement can freeze, turn into ice crystals, and your concrete strength is essentially zero. You have to remove and replace in most instances that are that bad. Now, anywhere along that spectrum, if the heat isn't where it needs to be, the hydration reaction will slow down. So the strength gain won't be as quick as you'd like. You won't be able to open it to traffic as quick as you might like. If it gets too hot, I wish I had a dry erase board. There's problems that happen on the other end, but they're more difficult to describe without drawing. But too hot is a problem as well. Curing objectives. So we're trying to prevent or replenish the loss of moisture and to maintain a favorable temperature, one that's conducive to proper strength gain. We're doing this for a predefined period of time. As a contractor, the owner can't expect me to cure this concrete slab for a year. It needs to get open to traffic, usually very quickly. So we have a certain amount of time that we're most concerned with. What we see in these photos are the two most common curing methods in the US. The first is an application of a white pigmented curing compound from a texture cure machine. So it's a very automated method. Our Federal Highway Administration's guidance is that the surface, if you're using white pigmented materials, should be as white as a sheet of paper. And that anything less is an indication of serious under-application of the curing compound. So this could be water-based, a wax water-based material, or it could be a resin-based material, which is increasingly common. Over here we have blankets, which are just like a blanket that you sleep under. It's holding in the heat of hydration to help maintain a favorable temperature. We do that if it's cold out. So we do have different methods, that's two of them, and we break them into initial cure and final cure as well. An initial cure is something that we might do during the point before bleed water has escaped completely, before we can apply the curing compound or other methods. Now, when we place the concrete, I guess we didn't get into that detail. There is some water that will bleed to the surface. We'll get a nice sheen at the surface, which will evaporate off. Before that's completed, we cannot apply a membrane-forming curing compound. Otherwise, the bleed water will mix with it, and it just goes away. It's not effective. So before we are at that point of the bleed water happening, we can use evaporation retarders on the surface. So we just spray those on the surface, or misting or fogging of the surface. So we're not adding water to the system. We're replenishing the water that's evaporating out to try to prevent plastic shrinkage cracking. Once we get past that point, the final cure, we can use wet coverings. So that might be a paper or burlap that we continuously keep wet. We're trying to moist cure. We can use impervious paper to try to seal in the system. Plastic sheets for the same reason. We can even go so far as using steam or electrical heating, adding a bunch of heat to the system. And we'll do that in extreme climates like Minnesota and Wisconsin. We actually have massive heated blankets that we roll out onto the grade, and it heats up the soils or the subbase. We place the concrete, and we roll that same material or that same blanket right on top of the concrete to help add heat to the system. That's the only way that we have enough time to build concrete pavements in such cold climates. It's by extending it with our curing. Membrane-forming curing compounds, like this white pigmented, just try to seal the surface. Insulating blankets and linseed oils, which are more commonly seen as sealants They fill the voids of the concrete to help resist freeze-thaw issues. Most common are the membrane forming and the blanket cures. Is that true here as well? You're transitioning to the resin-based, correct? And less of the water-based? That's only our harshest climate state agencies are really pushing for the resin. In fact, Jeff Raessler has done some preliminary research at the University of Illinois, and he now suggests that if we cure too well with the resin-based, we might increase curl. Because what we do is we create too fine of a pore structure, which means for the same drying of the environment, we cause more shrinkage potential right at the surface. So where curing has been, you're nodding your head, where curing has been for 100 years may have been the best deal, and to further seal the system might actually have a negative consequence. So keep an eye out for that if you see it with the resin-based here. We're watching all the resin states right now to see if there's any proof of that in the field. But that's based on research with specimens that are this big inside of a controlled lab chamber, and you can only get so close to reality with that sort of approach. Here's some photos of good curing. Of course, this texture cure machine will do the best job. We're going to get a nice coverage of the surface and the edges of the slab, all the exposed surfaces. If necessary, we'll use a hand sprayer. Same deal, though. You want to have the surface as white as a sheet of paper. Now, these guys must have known this photo was being taken, because you don't usually see it quite that good when it's being sprayed on by hand. You usually see something more along the lines of this, which is marginal, or these, which are poor. You can see distinct marks where the nozzle did work in a very concentrated fashion, so you want to get past that point and have a more uniform coverage. This is a texture cure machine application. You can see, and this was in Texas. They just have trails from where they tried to cure. A lot of things could cause that. Maybe the equipment wasn't clean, the nozzles weren't clean. It could have been the consistency of the material at that temperature. It could have just been they didn't have the nozzles open enough. It's hard to say. But we've had some practical research come out of Texas on the curing application side of things, because it's very difficult, based on the manufacturer's recommendations, which are a certain area of application per a certain volume of material, to try to enforce that in the field. So the California DOT first developed what they call the diaper test, where I don't know if you have these here or not, whenever you're training a puppy, a small dog, to go outside, you put these sheets out, and the dog pees on those, so just absorbent sheets. So we'd place those in the field, run the cure across it, and we would measure how much material was absorbed over that area, so we could check the application rate. The easier thing seems to be, if you're using a texture cure machine, to validate each piece of equipment as the owner independently. And that's the automated method, not a hand sprayer, but the texture cure machine, such as this. What you can do is, on each nozzle, just hang a bucket. You can have them move forward at the rate that they would normally move forward with the nozzle spraying, and measure how much curing compound is in each bucket. And based on the amount that's in each bucket, look at the handle that controls the forward speed and put a mark that they can't go past. Because if they go any faster than that point, the application rate will be too slow. So it's a very practical, hands-on way to say, well, we're going to validate your machine, your piece of equipment. The only other caveat from my time in the world of contracting is be happy that you're into the world of resin cures, because with water-based cure, it was very common for the contractors to just add a little bit of water into the barrel of curing compound to help extend how much is left, because it would just mix in. You can't do that with the resin-based materials, so there's no way to cheat the system. Blanket insulation, we place this after we've sealed the surface with a membrane-forming curing compound. It reduces the loss of heat of hydration. It also lessens some of the other effects, like the air temperature and any sort of evaporative cooling that would happen from wind and solar radiation, so the sun's heat. So we might actually insulate sometimes if the sun is too hot. Typical thermal resistance, our values down there. Now, when do we use these? A simple table based on the ambient air temperature and the opening time to traffic. When we might consider, yes, we would use blanket curing. So more often than not, it's for early opening to traffic than anything else. We're trying to get the hydration to happen in the window of time that we're most looking for. Now, of course, you can change the cement content. You can change other factors to promote higher release strength. This is just one consideration. Good practice here on the left. They were blanket curing long enough to peel them back in time to saw cut the joints. This photo on the right, I took in Washington, D.C. in January of all times, which one of the worst times in Washington, D.C. to be constructing concrete pavements. They were rebuilding an intersection a quadrant at a time. I watched them place the first two. They worked okay. In this particular case, the curing just came off almost immediately. Jointing. So we've built the concrete, textured it, cured it. It's time to saw cut the joints where we want them. If we have embedded steel, we've somehow communicated to the saw cutting crews where we should be placing the saw cuts. Here, that gentleman is dragging a piece of chain or rope across the surface. And they're doing that at a regular space to help indicate where to saw. We do sometimes see formed joints like we see in the top right here. It's not too common anymore. It's common more in developing countries, it seems. The problem is whenever you have a perfectly flat piece of concrete and you somehow induce a void of some sort, the material has to go somewhere. It's just like inserting the tie bar into the side and making a hump. You push down and create a void, you end up with a little tiny hump right on either side of it, which makes roughness. So it's much better to wait till the concrete sets and then to saw negatively down into it. Sometimes we have massive devices like this that follow the paving, and right on top of the pavement, that's called a span saw. So we'll do the entire width of the pavement all in one pass in very automated fashion. Otherwise, more common, we'll see early entry saws, whether dry or wet. There's a soft cut saw, or a conventional wet cut, which is quite a bit larger. And we saw cut those much later than these early entry. I see we have a distributor of some of these sort of technologies over there. Saw blades, most common are industrial diamond blades. They require water cooling to keep them cool, or you can have an abrasive blade. It's a massive saw at a military installation. We have to match the saw blade to the type of concrete that we're sawing in. It's the same as it is with the diamond grinding and grooving. The aggregate hardness will impact the type of blade that we need. Luckily, it's a relatively controlled approach that the different suppliers and manufacturers have developed. They'd be able to help you with those sort of challenges over there. Order of saw cutting. Cut the transverse joints first. When we build this very long, continuous stretch of roadway, it's most restrained in that direction. It can kind of shrink and contract across its width relative to its length. So we need to prevent the cracking in the long direction first. So we saw cut across the width first, the transverse cuts. It's best, though, to keep the saw cutting operations as close as possible to each other. So that's the transverse and the longitudinal. When it comes to high volume road production, it's very common to see a jig like this. It just references the outside edges of the pavement. It has casters or rollers. And even as we move into turns or anything else, it maintains that saw right at the middle of that width. And we can gang mount those. So we can mount 2, 3, 4 saws on one of these types of jigs. We'll see that when we talk about overlays. If everything went well, here they have a point where they've indicated this is where I want you to saw cut. This is where I place the dowel bar. We can see our transverse tine. They've saw cut down to the required depth, and the joint is activated. That's what we're looking for. The joint on the right's a little bit finer of a crack, but it's there. Now, the depth of the saw cut is as important as its timing. If we cut too shallow, we might not create a weak enough plane. So the concrete might not be able to crack at that point. If we cut too deep, we end up getting rid of the aggregate interlock, and that's especially important if you're not relying on dowel bars. So you don't want to go too shallow or too deep. If you go too deep, you also wear out the equipment a lot faster. Part of the challenge is, especially with the abrasive saw blades instead of the diamond-tipped ones, is as you saw more and more, the diameter of the blade will start to decrease. If you've ever used a Dremel, a handheld Dremel with the cutoff blade, same thing happens with these. So the diameter decreases, so they have to cut just a little bit deeper in there to get the same depth of saw cut. And that's part of the art of the saw cut operator to handle all of that. Transverse joints, if you're building on an unstabilized material, you usually cut to 1/4 of the depth. Longitudinal joints, if you're building on an unstabilized material, usually cut to 1/3 of the depth. If you're building on stabilized materials, so a lean concrete or cement-treated base, you'd cut both to 1/3 of the depth. There's more friction, more restraint, and just to make sure we create that weakened plane, we cut a little bit deeper. And there's a note here on concrete overlays on unmilled asphalt. And we do this all the time in the US now. We'll take an existing asphalt roadway that crossed its width, it has some grade issues, and it has rutting, and we'll overlay right on top of that. The challenge is that we're looking for, say, a minimum of 15 centimeters of thickness, so that's the minimum. Where we have the rut, if the rut's an extra 25 millimeters, well, then the slab is 175 millimeters at that point, which means to maintain the same saw cut depth, we have to actually cut a little bit deeper. And we do that with our overlay operations. The saw cut operators will dip the blade down just a little bit deeper right where the ruts are. That's all part of the understanding of the contractor on the detailings of that particular construction and the inspectors to make sure that it happens. But we do that and it does work. Yes, I have a question. Do we have the handheld mic? Does that one work? I got to turn it up. As we're getting the mic. Or do you want to ask it in English and I can repeat it?
You're talking about deep?
Yes.
Depend on early entry or not?
Oh, yes. I don't know if I have a slide on that or not. Yeah. So he's asking if the saw cut depth is in any way related to the use of early entry sawing or not. Short answer is yes. Should have just asked you since I know you speak English. We'll get to that in the next slide. So there is a minimum saw cutting depth. The short response is that the mechanics change when you're cutting so early into the life of the pavement. So it's not as simple as this is what we know works from 100 years of experience, and we introduce a new technology that cuts at a different time. Well, we can actually saw cut a little bit more shallow because we're so early in the life of the pavement that the mechanics are different with crack initiation and propagation.
¿Y cuánto menos el espesor?
How much less is the cut? Yeah. Early entry saws, well, I guess I don't have that. Generally, we're talking metric. That's the third thing that the US school system does not teach very well is metric units. It's about 30, 35 millimeters minimum. Does that sound about right? For early entry. 25 minimum? Yes, yeah, I know that. But it's about 1.25 inches, 1.5 inches typically that we're at for, depends on the specification. For the minimum. Okay. So 33 minimum. Does that sound about right? I guess we have the manufacturers over here. We could ask them. Ask them during the break. But yes, there is a difference. So whenever we're sawing, we also can't go too quick. If we have a harder aggregate, it might take slower speed for the sawing operation to be effective in essentially allowing the saw blade to rest deep enough into the cut. If we push that, and there's usually a self-propelling mechanism inside these large saws, if we push past that, what we're going to do is push the saw blade up because it's constantly cutting this curve, and it'll start to rise the cut up into that, which means it won't cut as deep. So we have to constantly match the sawing blade and speed and all these things together. If we don't cut deep enough, there's a risk for cracking. Starting and stopping requires particular attention. Now, this is on the early entry, the other detail that I wanted to get to. A conventional saw is what we call a downcut saw. So a wet cut saw cuts in this clockwise rotation. This is another one of those seemingly unimportant details in design and construction that matters. Now, when this is cutting this direction, and it comes to this free edge, I can't get too close to that speaker, what happens is we're cutting into the slab. So it's always a supported cut. The early entry saws cut the other direction, counterclockwise. So whenever they come to this free edge, they work to push or blow out that free edge because there's no sort of support. Once it gets to the point of cutting right here, this little tiny wedge wants to just push out. So you can end up with blowout of the edges, and this is particularly of interest at intersections of cuts. So if we already cut this direction, they manufacture plastic inserts I would put into that first cut before I cut the other direction to help provide some support or constraint. Otherwise, we stop the cut about 13 millimeters from the edge of the pavement to prevent this sort of blowout. Now, if it's windy out, it's best to cut with your back to the winds. And again, this is all a big system at work. The concrete, as that sponge, wants to dry out if there's wind, evaporative cooling, and a loss of moisture from the surface as the wind passes over the surface. So if you have a strip of concrete, say this is our concrete road, and the wind is blowing this way, it's going to dry out this side. This side wants to shrink, whereas this side is not as dried out. Now, if I were to cut from right to left then, I'd get to a point here where it might be the case that I get close enough to the edge and the concrete just cracks while I'm cutting because there's so much restraint, so much shrinkage wanting to happen on that one side. Now, if I would have started my cut on this side that has shrunk and cut the other direction, I don't have that same effect. It's another minor thing. Contractors are always watching out for this stuff because it happens once or twice, you lose a little money, you learn to watch for those things. We have to make certain that the saw cut that we've made is clean if we're going to seal it. And it's more and more common to see unsealed joints. There's less evidence that they makes a difference than conventional wisdom would have you think. But immediately behind saw cutting operations, we'll generally clean this out. I guess after the widening cut, we'll clean that out. And immediately prior to the sealing operations as well. We're just trying to remove any sort of debris that might be in there. But the cleanliness of both faces is important. We can't bond a sealant to a face that is dusty or unclean. A simple wipe of your fingers down into the saw cut can give you a visual indication of if there's concerns or not. In fact, we now have a simple field testing kit that has been developed inside the US. I don't think I have photos of that here, but we're taking tongue depressors. It's very, very simple. Tongue depressors, so what the doctor would use to push down on your tongue, just a wooden stick, a piece of black t-shirt, cotton black t-shirt around the tongue depressor, Stick it down, wipe it around. You can see where you can't see with your eyes. And we're also doing, for the sake of adhesion, we're using electrical tape, so 3M brand electrical tape. The same thing, tongue depressor down. We push it against the faces of the concrete saw cut itself. And then we clamp on a fish scale. So little lightweight scales that you would bring fishing to see how much the fish would weigh. And we pull that out. And we measure the maximum load before it gave. And that tells us, well, it's good enough that we can adhere a sealant to it. So just simple field tests that have been developed in the last couple years to check this. Because if you're going to seal the joints, you have to make sure that they're clean enough. Otherwise, the entire point of the sealing it's pointless. You shouldn't even be sealing if you're not going to make sure it's clean enough to seal too. They will not perform as you expect without proper preparation. To drive that point home, from an owner's perspective, it costs the contractor nothing more to check this and do it correctly. What you see here is the relative cost, so basically the percent of total cost of each of the sawing operations. We have a silicone sealants, hot pour sealant, so that's an asphaltic material, and a compression sealant. Now the blue bars are our initial saw cut. That's the blue. The red bars are the reservoir saw cut, so making it wider to get the proper aspect ratio. We'll touch on that in a bit. The green bars, the smallest, are the cleaning. And the purple is furnishing and installing of the sealant. Cleaning is such a small part. To have to do it twice, from an owner's or inspector's perspective, just make them do it twice to make the sealant actually last. All right. I said widening cut because you have to look closely at this photo. The lowest cut that we see there is our initial saw cut. So that's as narrow as we can make it. What you see over the top of that is a widening cut, which was done so that we could create the right design detail here in the field. Because the engineer is making this a certain width and depth based on the sealant that is being used. The contractor is just building what the engineer wanted. So we first make that crack control cut. That's the deepest one. We come in, we widen that. We clean the entire faces. We make sure that it's clean. We will install a backer rod. It's like it's pushed down with this little wheel to the right depth. And we install that to help control how much material that we're placing into the joint itself and to create the right aspect ratio. So the correct width to depth for the sealant itself. So if we have a sealant, say it's very wide and narrow like this, and we pull on the two ends, it's probably going to want to tear in the middle. Now if we turn the sealant the other way, it's very deep but narrow, and we pull on it, it's not going to tear in the middle, but it'll probably rip away from the faces of the joint. That's why we have this specific width and depth. We're balancing that because of the mechanics of a sealant. We don't want it to break away from the sidewalls, and we don't want it to rip apart itself. So the manufacturers provide the guidance to the designers on how to design that specific detail. It's just getting translated into the field. If we're using a flowable material, this backer rod also allows us to push against something. So if we push on the sealant, the backer rod pushes back. And it prevents three-sided adhesion, so that our sealant is really only sealing between the two sidewalls. That's what it's designed to do. It's not designed to seal on three sides. And we seal the joints following the manufacturer's recommendations on the minimum installation temperature. Again, we make sure everything's clean and dry before we seal. We fill the sealant from the bottom up. If you try to seal from the top down, it can entrap little air bubbles. From the contractor's perspective, that's good. It uses less sealant, but it's not actually sealing much if there's a lot of trapped air. And this should be as smooth and continuous as possible. And the particular installers, the people who use these sort of pieces of equipment have a very good eye for this, and they're a very constant rate. And it's impressive to see. Transverse construction joints. So that we'll build the pavement. That's a normal day's work. But now we're at a point where we have to stop paving. So this is a break in the operation, whether it's from the end of the day's paving or we had some sort of material disruption. We couldn't get concrete because there's a traffic jam or something on the way, and we have to stop paving, or even because it's raining outside. We just have to quit. We can either form these if we know that they're coming, so we create a formed system, or we can saw them. In either case, there's no way to account for these in the layout. You can't, as a designer, tell the contractor, we're going to have transverse construction joints in these 5 spots and nowhere else. It's next to impossible. So this is part of why the contractor needs the ability to adjust things in the field. And it's best to match transverse joints in the adjacent placement if you're paving next to existing concrete. So if we have a lane that we've already placed, we're going to want to put our transverse joint right there where it matches the existing pavement. If we do what we see on the bottom, we're going to have to saw cut a joint in that existing, or adjacent to that existing slab, tie bar into that, and saw cut another joint there. And it just creates one panel that's weaker than the rest. It's all about uniformity. So in this case, you might pave to there if you're sawing back. But you wouldn't pave to there to think that that's the best place to stop. This is what a formed header looks like. This can be a 2-part form with dowels or tie bars protruding through. So what we see here is stakes vertically. They have one piece of lumber and the exact same height there, both of which have semicircle notches to help support and align the dowels. And then there's the exact same thing flipped upside down with the semicircle notch there, all temporarily held into place. We could also do this through what's called a false form. We see this more in industrial concrete paving, where we have essentially a pocket or a sleeve. So we could have the piece of lumber here, but instead of having an actual dowel bar there, we could have a pocket nailed to that. So we could remove that form and then just have a hole to stick the dowel bar into. So there's a couple different approaches that have been developed. But if we're building them like this, we have to make sure we get good consolidation into those corners. Because the problem is especially if you're slip-form paving, the concrete paver will have to lift out before it gets to the end. So the vibrators aren't going to touch this concrete. This has to be manually vibrated or consolidated. Here's the formed header that I got to see them build in Indiana because the rainstorm was approaching, and it was decided that this was the route to take the day. Now I think in this case they were about 2 hours into the paving. And the position that I have, or that I had with ECPA, I suppose, these were the days that I learned the most. If you go out in the field as an engineer and everything's going well, it's cool to see, but you don't learn that much. When the day goes terrible for the contractor, that's whenever you, as the engineer, learn how to actually solve the problems. So we have another question. Pregunta? ¿Es aquí? Thank you. So on this particular day, I think they were 2 hours into the paving. They thought that they were going to have a good day. But this, because the way that labor unions work, if someone shows up onto the job site, they're paid for the whole day. So this is a heartbreaker for the contractor. Yes, sir.
Alors, No he visto diamond dowels. ¿Ustedes usan diamond dowels en pavimentos?
Yes. We use diamond dowels in industrial all the time. We use them now in airfield pavement. For roadway pavements, I've not seen them outside of roundabouts in places where the shrinkage isn't lineal. Does that make sense? So yes, I think that we'll see them more and more inside of roadway applications. It's a technology that has developed in the industrial space. Now, the reasons, just briefly, all of the real dowel innovation outside of materials, so this is very loud. Aside from a zinc-clad dowel bar or these other anti-corrosion measures that we're seeing, the geometric changes in dowel bars have happened in industrial pavement design because in the industrial markets, the loading has moved from large pneumatic tires on forklifts and other devices to very small metal and plastic wheels, which made it such that any differential deflection at the joint became very problematic and caused spalling. So the doweling manufacturers, specifically in that space, have developed these devices to be more of a means of resolving bearing stresses and limiting differential deflection. For roadway traffic, even if there is some differential deflection, everybody has pneumatic tires. They have air-filled tires, so it doesn't create the same sort of problems. But we're now seeing those technologies, as their cost comes down, into the roadway markets. Because of time limitations, we'll get to some industrial stuff later. It's very, very small, though, because most of the square meters in the world aren't industrial. So the tone of today's discussion is focused on the roadway side of things because that's the largest application, and it's also the most well understood. We build the roadway, we paint stripes on the roadway, people stay between it. That's a controlled problem for construction and performance. Industrials, I could talk for 2 days straight about the challenges there. Much more project specific. So this is a formed header where they knew that the storm was coming. They popped in some of that false formwork in around this dowel basket and then just cleared back to it. A lot of hand finishing. The last option for a header is a sawed header. So in the bottom photo we see, they just paved through. Continued paving. They knew they were going to saw back. This is bonded on asphalt. You can see the asphalt pavement down there. So they paved until they ran out of concrete. Full depth saw cut, some space back. And we drill in and epoxy dowel bars into the backs of those holes. So that's another case like the sealant, where we drill the hole, the grout that we're installing the dowel bars with, or the epoxy, we have to start that injection at the back of that hole. If you just put it somewhere around right at the front, and you stick a dowel bar in, there's air entrapped there, which will just make the epoxy just shoot out the front without it actually getting to the back, because you create a sealed system. Opening to traffic requirements. Now, these tables were developed by Applied Research Associates based on having essentially zero fatigue damage in the concrete pavement. So they're based on fracture mechanics, so they're thickness dependent, support dependent, and load dependent. So here we see the required flexural strength for construction equipment. If we have thin slabs, we have different values than if we have thick slabs. Depending on the foundation support K value, it's not a design day, so we don't get into this too much, but the stiffer the support, it makes a difference. To support a span saw, if we have a stiffer support, we can get away with a lower flexural strength. And then here's to support 151 kilonewton tandem axle load. So that's probably something like a water truck. 10 repetitions or 50 repetitions to cause zero fatigue damage. Same thing for public traffic. And it depends on the number of repetitions, again, the thickness of the pavement, and how stiff the support is. But we don't see particularly high loads here, or high strengths. We're talking about half the typical 28-day strength in most instances. Not particularly high. So just know these tables exist, reference them if you get into a case where you're trying to specify a minimum flexural strength. And again, if you need to convert those to compressive strength, there are readily available equations out there. So to determine the strength, we can use the flexural or compressive. Flexural strength is a lot more sensitive of a test, especially at early ages. It's difficult to conduct in just a couple of hours, and sometimes we're talking about opening the traffic in 4 to 6 hours. To try to get a flexural test to the testing site, the molds are removed and everything in that amount of time, it's very difficult. Those are fragile specimens. So in most cases, we'll use compressive strength, or we'll use the maturity method. If we're using compressive specimens, we do need to field cure them. Because what we're trying to assess is the strength of the concrete in place. If we construct it overnight, and we intend to open traffic in the middle of the next day, and somehow the day ends up being colder than we expect it, the concrete won't hydrate as we expect it. So to take a specimen from the time of construction into a cured chamber and to break it is not at all representative of the actual field curing. So we need to make sure the specimens are cured right alongside the pavement. And otherwise, we can use the maturity method. If the opening strength cannot be met with conventional mixtures, we can use high early strength concrete. So here we're changing to type 3 or HE, high early strength cement, adding more cement content to the mixture, 400 to 500 kilograms per cube, changing to a lower water to cement ratio as low as 0.37. I'd say we go even lower now with the types of admixtures we can use to get there, 0.35 or lower sometimes. Use a higher concrete mixing temperature with heated water or aggregate. Actually introduce heat into the system before we place it to help encourage hydration. We can use accelerating admixtures, insulating blankets, any approach you want to get it open in the amount of time that you're looking for. But it's not at all uncommon now to see high early strength concrete mixtures. It's important to note, though, that these tend, because of the measures that are taken, these mixtures tend to cost more than a conventional paving mixture. So if you're paving a big area or even an intersection, that last little critical bit is what needs to have this mixture. If you're paving overnight, you're going to place a lot of concrete. And the stuff that you first place in the evening will probably have enough strength versus the stuff that you place in that very last window of time before opening. So when it comes to optimization and minimizing the cost, considering these more expensive mixtures only when necessary will lead to the lowest cost to the owner. Any questions to that point? Yes?
It's very common.
I can, well.
It is very common the use of admixture like accelerating. Yes, in pre-mixed concrete.
No. That's because if anything, we're trying to extend the work window as much as possible. Yes, only for these high early strength. We'll use it for, say, dowel bar retrofits, which we'll talk about. So whenever we're reinstalling load transfer devices across joints, we'll use it then because we want it to open to traffic quickly, or repair patches. So in those cases, yes, we have a very short pot life, though, because we're mixing it in the field, dumping it, and covering up and texturing it as quick as possible. For a typical pavement, you have to transport the material. There has to be time to place it. No, it's not common at all to see them. Any other questions? Okay, so paving in inclement weather. We'll start with cold weather paving. I arrived yesterday in shorts, and Mauricio corrected me that it's not shorts weather in Santiago this week, so I learned that lesson, that it gets a lot colder here than I suspected it would. I also looked up the weather for Santiago. The airport was much colder yesterday morning than the Weather Channel said it would be. So cold weather paving, potential problems. The hydration reaction is going to happen a lot slower. That's our biggest challenge. So it's going to slow down strength development. If it's thick enough section, the thermodynamics of the cooling of the surface versus the underside is non-uniform at all. In fact, the hydration at the bottom will heat up the bottom, and the surface might just continue to cool off. So you end up with differential shrinkage and differential stresses because of that. And that can cause a lot of problems with how the temperature sets into the slab even. Because when the concrete transitions from the point of plastic to hard, the temperature curve that happens inside of that locks into the slab. So you can end up with different curling and warping issues because of this particular challenge. So some mitigation steps when you're paving in cold weather. First, you shouldn't ever pave on frozen subgrades. If we know that there's visible moisture, if there's frost or snow or something else, just pick up some of the aggregate and see if they're frozen together. It's that simple. Especially with how dense of a graded aggregate as you have to get to that CBR value. If water is going to get trapped, it's going to get trapped at the surface. You're going to be able to see if it's frozen or not. Don't use frozen aggregate lumps. That goes back to the loader operator at the batch plant. Same thing happens at that location nearby as it happens to the subbase. When they're going to mix the concrete, if they have big lumps of aggregate frozen together, it's not going to mix very well with the rest of the materials. You can use a higher cement content. It just helps jumpstart things and get the heat of hydration more in line with where we want it to be. Use the accelerating admixtures, again, not very common. Can use these blanket cures to help trap in the moisture. And we can even heat materials. So I mentioned that app earlier, the concrete temperature analyzer. But here's a case where they've heated the materials enough to get the temperature to where they want, and things are steaming as they're placing that concrete. I guess there's one other mitigation step there. Don't pave yet at all. Just wait until the weather gets a little bit better if it's at all possible. This is, in the extreme cases, you don't have much of a choice. More often than not, for me personally, the projects that I got involved in where this was a challenge, cold weather paving, were military applications where it wasn't a matter of, well, we can wait. This has to be built today. So if you can wait, wait. Hot weather paving, some of the potential problems that we have there. Moisture loss during hauling and placing. So as we're transporting the concrete, there are tarps we can pull over those transport vehicles to prevent the sun from beating down on them and to prevent the wind from pulling moisture out of that. That's when we talk about roller compacted concrete this afternoon, that's a much more important issue for that than conventional concrete. But it's still important for conventional concrete. The aggregate stockpiles will do the opposite. They won't get moist and freeze, they'll dry out. It's very hot out, the sun's out, things dry out. That will affect batch-to-batch consistency because it dries at the surface of this big mound of rock, and the loader operator takes a hunk out of the side, but what's inside the middle might be moist while the surface is dry. So batch-to-batch and within-batch consistency gets greatly affected by that. That's part of the loader operator's job, again, to just cross-blend things, continuously work the stockpile to make that not happen. In many cases, we'll have sprinklers out there just wetting the surface of the stockpiles. Subbase dries out and absorbs moisture from the slab. That's another challenge. So we talked about that, moisten the subbase before we place the concrete. The dark subbase, such as an asphalt layer, can heat up, causing more differential stresses. Instead of the surface cooling off because it's cold and the bottom staying at a normal temperature because of hydration, this just shifts that temperature curve higher. The surface does what it typically would do, but the asphalt beneath has supplied extra heat. So there's that differential. Rapid evaporation causes plastic shrinkage cracks. It becomes difficult to entrain the air at higher temperatures. Concrete sets more quickly, making finishing difficult, and the sawing operations must proceed more rapidly. So, too quick? My apologies. Hot weather paving, steps for mitigation. Begin curing as soon as possible. We want to seal that system with our curing compound, put the blankets on top, whatever we need to do. For hot weather, we're more talking about sealing of the system. Here we say it very abruptly, don't pave on hot days if possible. If it's too hot and the project can wait, there's more problems than good. Things just become very non-uniform. Maintain a uniform stockpile. I mentioned that. The loader operator will continuously work the materials. We'll put sprinklers out on the stockpiles to maintain the surface moisture content. We can use retarding admixtures to slow down the hydration reaction. So we have more time in transport, more time to place the concrete. It doesn't set up as quickly. We can use more of these supplementary cementitious materials, or fly ash and slag cement. That lowers the cement content. We end up with the same or better ultimate strength, but we have a slower strength gain up front. So this is useful in hot weather paving. We whitewash dark colored subbases, such as our asphalt subbases. We pave in the morning if we can, or in the evening or at night, not in the middle of the day, where the sun's heat is adding heat to the system very quickly. Can increase the dosage of air entraining admixtures if we're having problems keeping air. We need to make sure we keep the subbase forms equipment and everything else that touches the concrete damp. Even when we're transporting, if we're using those rear end dump trucks, right before they go to the batch plant to pick up the concrete, we'll oftentimes just spray out the inside, not just to wash the surface, but to cool it off some. We can use temporary sunshades or windbreakers. When we have the international practices presentation next, you'll see a case in South Africa where they're just dragging a tent along behind the paving. This photo, that's not mine. I believe that's from the American Concrete Institute, and it's of the addition of dry ice to a ready-mix truck in United Arab Emirates, where it's so hot that they have to have some other means of just taking the heat out of the system, otherwise there's no way they can build. Rained-on pavements. Some of the irony is that the environment created during a rainstorm, when it becomes relatively cool and very moist, is an incredible curing environment for concrete. Think about the moist cure chambers that we cure specimens in. Right before a rain event is about as close as we get to that without being moist. But as soon as the rain happens, we have problems like this, erosion of the surface. If the rain occurs before the final set, we can have these sort of imprints and a washing away of the paste. And if the rain occurs after the final set, we can have rapid cooling of the system, but really right at the surface more than the bottom side of the slab. So the surface wants to contract. If we haven't yet solved the joints, we have differential stresses develop and a higher risk of cracking. Here's a bad example, I guess a good example of the bad. Now, part of the problem is when you have a rooftop or any sort of super elevation to the roadway, all of the water that falls in that tributary area builds up speed as it moves towards the edge. And it picks up sand from the concrete, from the mortar. So by the time it gets to that free edge, it's very much like a river that's picked up a lot of dirt, and it has a more erosive force than just water. So it tends to eat away the edges a lot more. Now if we're slip forming, sometimes we will immediately install an edge form as quickly as possible. So we'll have plywood or some other lightweight formwork readily available to just stick up against the edge of the slab. I believe I have a photo of that and a very bad example soon. Sometimes we'll have to saw cut this back to get rid of that particularly bad area, if it's bad enough. Now, the problem doesn't extend into the concrete much. It's this near surface issue. So we like to see that system more diamond ground or the surface texture somehow removed if it's objective. But in many cases, as long as the water to cement ratio isn't appreciably changed at the surface, this is treated as an exposed aggregate surface. And I understand it's not what the owner has purchased. They're not happy with it. So there's sometimes a concession in payment to the contractor, but removal and replacement is a very If it starts to rain during paving, most of the texture cure devices and the slip forming operation will have a big roll of plastic. I'll look out for that. I saw that in some of the photos we had for tining. But they have a big roll of plastic, so as soon as it starts to rain, they will pull that out and cover up the fresh concrete that has not yet set. So the contractor should have some contingencies in place in case this does happen. But as soon as the surface texture sets and the cure has applied, they're covering it up with plastic. Oh, there's a roll of plastic. So that's part of the texture curing machine. We have our tines right in the front there. So we protect the surface if possible. We should expect, as this photo on the right shows, some marring or discoloration of the surface if we cover it up with the plastic that early in its life. It's just part of the expectations, but if this is discussed in the pre-paving meeting between the contractor and the owner that this is the approach to take, part of that dialogue is the understanding of implications of it. So again, that finished surface with rain changes the water to cement ratio. It does give us a less durable surface, so you could have crazing, scaling, or dusting of the surface. So in big enough projects, we'll see cores taken and petrographic analysis done right at the surface. They can't tell you the water to cement ratio of that set concrete, but they can tell you indications of the hardness and other factors that might come into play. Talked about diamond grinding and the cutback. Nighttime paving. We might consider this to mitigate hot weather, minimize the traffic disruptions, maximize production rates because we're not dealing with all of the public traffic that happens. We need to observe the precautions such as safety meetings. They become especially important to make sure that everyone understands the risks at play, discuss traffic control, ensure that we have ample lighting, which has become much less of a concern in recent years, that these sort of high output lights are much less costly than they used to be. Of particular importance, a subscription to a weather service. When we're paving during the day, we can see if a rainstorm is coming. At night, you have no idea what's happening. So from a contractor's perspective, knowing the risk for bad weather, whether on a laptop or a subscription service on radio or something is useful. We have to maintain the haul roads during the day because at night they will get beat up. So there's that aspect on the other direction than the usual operation. And saw cut timing becomes somewhat of a challenge sometimes if we're paving at night. Just because of the typical duration between placement and saw cutting operations, our saw cutting operations can be at very strange hours, which sometimes drive up their cost if that's an activity that the primary contractor is subletting out to a sawing crew. I guess this is the last one of the ACPA's free trainings that they've developed with FHWA recently. This one is on best practices for constructing smooth concrete pavements. So as with any of those that I've mentioned, they're absolutely free. Unfortunately, they are only presented in English, but there'd be, I think that one's about 3 hours of lots of detailed guidance on all of the things that impact pavement roughness and what you can do to counteract them to build the smoothest pavements possible. Troubleshooting, here's that really bad photo where they're putting up false formwork because the edge slump is all over the place. That's a project that they are clearly having a lot of challenges on with the concrete. Troubleshooting, though, it's such a massive bubble of scope creep. Once you start talking about one problem, it goes on to the next. And it's very much the case that it's not usually one specific smoking gun causing the problem when it comes to construction-related issues. And there are people that have made entire careers out of troubleshooting problems in the field. So we can't really get into all the details. I've given more precautionary guidance of things to look out for. So we're not going to get into the detailed troubleshooting side of things today. We're going to transition instead to concrete overlays unless anyone has any questions. Any questions on paving operations, dealing with inclement weather, anything like that? Got to give them some soda at lunch to wake everyone up. So concrete overlays. What is a concrete overlay? In the US, we consider it part of a resurfacing family. It's not new construction. It's once the system's been in place for a while, and we're trying to either preserve what's there or overlay it, resurface it with something that will add structural capacity. That's when we're talking about an overlay. Now, when it comes to the sustainability side of things, this is about the most sustainable solution that there is. Anytime we extract what's in the field and reconstruct, we're hoping that the contractor will recompact the soils to a certain standard, and we're using new materials, new raw materials, and there's more disruption and energy use. If we have what's already out in the field, it's already well compacted from traffic. It serves as a reasonable support system, whether for concrete or asphalt, as long as it's not so far deteriorated that it's a poor support. So we can go out and on existing concrete or asphalt, place concrete on top of that. So we use this for intersections, rural roads, interstates, urban arterials, all over the place. This is the overlay guide. In the US, we've had 3 iterations of this. The version which I believe everyone here will receive a copy today was just translated by ICH into Spanish. This is one of those tech transfer opportunities through ISCP that ICH was interested in transferring of the knowledge, so they have stepped up and supported the translation effort. So this was the 3rd edition now, and it's becoming quite thick. We had the first edition maybe probably 8 years ago now. There was a lot of questions still from engineers after we wrote that initial edition, and we've had these other 2 editions since then. But it gets into all of the details, the types of overlays, how to evaluate existing sections and select which type of overlay is the best for your project, guidance on design, the various miscellaneous design details. Because one of the common comments you always hear back when discussing new technologies is, well, our case is just a little bit different than what you've explained so far, so it just won't work, which we've built millions upon millions of square meters of these overlays. We've worked out most of the technical challenges. So there's probably not a challenge you'll face that we haven't yet somehow addressed. Overlay material selection, dealing with work zones, whether it's a 2-lane road with opposing traffic or 4-lane divided highway, whatever the case is, there's guidance on that. Key points for construction, accelerated construction, even specification considerations. There's some guidance on specification language to help introduce the technology more easily. And then you can't build something without supporting it. On the repair side, there's guidance on the repairs for concrete overlays. The types of concrete overlays, you really have 2 for any given project. A lot of people that come out and talk about it say, well, we have these 6 overlays in this family. You have 2. Your existing pavement is either an asphalt pavement or a concrete pavement or a composite pavement, which would be asphalt on top of concrete most commonly. Now, depending on what you have, one of those 3, you can either bond to that existing system or leave it unbonded. If it's an unbonded system, for the engineers in the audience, we have a neutral access under flexure right at the middle of that overlay. And the supporting layer bends independent of that. What we see above that is the bonded condition, where the neutral axis, because of the bond between the two layers, shifts down into the depth of the concrete. And in fact, some designs have it such that the neutral axis is down inside of a supporting asphalt layer. So the concrete is always in compression. Concrete performs very well in compression, performs poorly in tension. Now, by shifting down that neutral axis, we can make that overlay thinner. That's the primary benefit of bonding. So let's first consider the top here. We have bonded, and we have unbonded. And this first example is over an existing asphalt pavement. Now we can see we have our ruts in our existing asphalt. We're just building right on top of that. If we have concerns for matching of grade or changing the elevation because overpasses or guardrails or any other ancillary details, we might mill the surface, so we do that a lot for highways. But if we can raise the grade some, we will just build right on top of the rutted asphalt. The unbonded overlay essentially treats that asphalt as an asphalt-treated subbase in design. It's just part of the support system. Now, if we bond to it and it becomes a composite, we then have to have a shorter joint spacing because of the added friction, the added restraint due to the asphalt layer underneath. So that's why you see the short slabs there. This is a fundamentally different design approach than the TC Pavement's OptiPave, which assumes an unbonded condition. But because of that restraint, we have to have a smaller panel size. Bonded over concrete. If we do an unbonded overlay, the new concrete assumes the existing layer is a subbase. So it would be just like a lean concrete subbase, essentially. Now what we see in that particular photo, they have an asphalt interlayer, and they've mismatched the joints from those underneath. And they've done that intentionally so that the weak point in the existing section, the joint, is in the middle of the slab, the strong point in the overlay. So this is just like a conventional concrete pavement on top of concrete. If we bond concrete on concrete, we're doing very, very thin to kind of repair the surface for some reason, and we have to exactly match where all of the joints are. So there's just these little differences and nuances. But all of these technologies have essentially been perfected. Bonded over a composite, pretty much the same as bonded over asphalt. And unbonded over composite is pretty much the same as unbonded over asphalt. 5 minutes? All right. These are increasingly common in the US. From the 1910s to the 2000s. Here's the number of projects that we have. Orange is unbonded and blue is bonded. We're seeing a very, very big increase in the number of bonded projects. I would imagine this in the 2010s, which we're just halfway through, or easily at over 200 bonded projects. It would be a very large bar. ACPA's developed this National Concrete Overlay Explorer, which provides you details on design and construction, photographs, just case histories of concrete overlays all around North America. We do have projects in Mexico and Canada in there. Now, in particular, this bonded on asphalt. This is one that we get a lot of questions on. This is no longer research grade stuff. People think that, well, initially we were targeting 5 or 10 year designs. I don't know how well the development of the technology has made it to Chile, but our federal government now says you can get 25 or more years of service out of these. We're targeting 25, 30 years, just like a conventional concrete, but we're bonding to an existing aged asphalt pavement. And we're doing it in a very thin section. So here's some good evidence that this is no longer research grade. This is an interstate in Kansas. They placed about 1.25 million square meters in one project. Very large project, 2 lanes in each direction, divided highway. and shoulders on the outside. So the design was 15 centimeters by 1.8 meters by 1.8 meters. So they did 48 kilometers long. They'd come in and mill out the asphalt down that 15 centimeters so that they wouldn't have to change the guardrails or anything else. They would clean and prepare the surface, install tie bars. We do not use dowel bars at all. The asphalt layer is not erodible, so it should not fault. We place the concrete on top of that. Here they're probing for thickness. They're doing their texturing, curing, all of that. Here's that photo of the gang-mounted saw. So they're cutting three longitudinal cuts at once. There's the final product before striping and opening to traffic. So we're talking about very large-scale operations here. I think I have one more slide, and then we're ready for the break. And because we have this new guide, I hope that people will take the opportunity to learn some about the technology. Maybe we'll have an opportunity for a day-long workshop specifically on overlays, which is something that we do a lot, but the environment is changing. We'll come back to this at the tail end of the day as well. Here's an example of Wright County, Iowa. In this particular case, they bid 125 millimeter thick concrete overlay, which is what was built, versus two asphalt options. They could do, one asphalt option. They could do 100 millimeters of asphalt on 75 millimeters of cold in-place recycling. They had 5 concrete bidders and 2 asphalt bidders. The concrete bid was 13% below the asphalt bid. So the cost, there it is in US dollars. They didn't mill the surface. Their planned overrun was about 10%. They ended up with 11%. There's a lot of counties in Iowa and around the US now that started to do alternate bidding like this to compare concrete and asphalt and to figure out what's the best value for the taxpayers. And it's especially a good way to do it as long as you can get comparable designs. But concrete can compete with asphalt now, even just on initial cost in many, many areas because of what's happened with the prices of concrete versus asphalt in the last decade. So we're at a good spot for a break. We'll talk about preservation or rehabilitation when we return.